Morning. So my topic, as Joe said, is adding persistence to Java. I have a standard usual corporate disclaimer slide, which my habit is normally to breeze by these and say, you can read it at your leisure. As long as there's a frame captured on the video, I'm happy. But I'm actually going to linger on this a little bit longer than I normally do this time. Mainly because I want to make clear that what I'm going to talk about here is not in any way an official Java plan. It's not the plan of record for Oracle, etc. So the fact that there's an Oracle logo on these slides doesn't convey official import to it. It's very, very experimental work and preliminary work. What I'm going to talk about is one possible approach to adding persistence to the Java platform that we've been investigating at Oracle. And I'll give you kind of the whirlwind tour of why we made our choices, the specifics of the model, a fairly high level, a very, very brief overview of how it might be implemented, and then I'll hopefully leave some time for questions and comments. So the challenge with adding persistence into Java is that Java is a very, very widely used programming language. There is knowledge in millions of people's heads as to how to program in Java, practices, tooling, methodologies, etc. And there's lots of existing code out there implementing applications. And so what are the goals of adding persistence to Java? And the particular goals I'm trying to work to are to minimize the disruption of current users' knowledge and practices. So this is trying to get something which they can adopt with relatively little training and change to the way they think about problems, and to maximize the ability to reuse existing code with minimal or no change. I think if you were trying to design something that was the best possible technical solution, irrespective of these, you'd probably end up with something different. But those are the constraints I'm working with. And so we need to address some questions. How are we going to put persistence there into the system? How are we going to express it and access it? There are a number of possibilities here. There are lots of possibilities. We could have special constructors for persistent objects that say when we allocate an object, this is going to live in persistent memory. We could make a special class for persistent objects and have everybody who wants a persistent object inherit from those. We could add annotations on classes to say which ones were to be persistent or not. All of these have been tried in various different cases, and all of these I've rejected for our approach as being non-orthogonal. And the idea here is that we want to try and maximize the reuse of existing code, and so we need to allow the possibility of an existing class to be used both in a volatile context as well as a persistent context with minimal change, ideally no change. And so all of these require some kind of change, and they limit the usability of the new class to some case or other. So we're not going to go down any of those paths. What's the model for consistency and recovery? There's probably, 1,000 papers on consistency and recovery techniques out there in the literature, and we could adopt some of the sophisticated, scalable transactional models at the object level, nesting, compensation, all of that stuff, something my colleague Bill is expert on, but that is also not the one that we've chosen to go down for this path. That stuff is all good and has nice properties, but it has the difficulty that it requires a very different way of programming from the standard Java way that people have adopted, and it requires different, fairly invasive changes to existing classes to make that work. And so we have chosen not to go down the path of a kind of a bottom-up transactional model. A leading contender for how to solve this problem within the constraints is persistence by reachability. And the idea here, I'm sure many of you are familiar with, is you designate some variables as persistent roots. And then everything that's reachable from any of these persistent routes is considered a persistent object. And in the same way that garbage collector traces out reachability, the runtime system would trace out reachability and make things persistent. This is entirely compatible with the earlier goals. There is lots of research on this from starting in the 70s, in fact, with persistent languages based on reachability. And in particular, there was a project that attempted to do this for Java. Well, attempted is perhaps not the right word, succeeded in providing a persistent Java implementation in the late 90s, just down the hallway from where I worked. So I'm quite familiar with that work and the people involved with it. And it didn't get adopted, as you probably know, as part of the Java standard. It became a side project, initially known as orthogonal persistence for Java, and then PJAMA, to not infringe any of the trademarks. And that's all well and good, but there's a particular problem I think we need to think about very carefully in adopting persistent programming. And the best explanation I can give for this problem uses these terms which come from, originally I think, from network protocols, and more recently from the recovery-oriented computing literature. And that's the notion of hard state versus soft state. Hard state is information that cannot be lost. It's something that you must at all costs preserve. And soft state is information that can be reconstructed from existing hard state. And traditionally, the way we've distinguished between these two is that soft state is in memory and hard state is on disk, behind an API in a file system, or perhaps even behind a process boundary and in another process managed by perhaps a database. This is an important distinction that I think we have to think about very carefully when it comes to persistent programming. How many of you recognize this gentleman and can predict what he is about to say? So this is a clip on YouTube from a wonderful comedy program called The IT Crowd, which if you've never seen, I'm sure you would enjoy. Let me turn it up a bit. See if I can go back now.
Hello, IT. Have you tried turning it off and on again?
So this is an IT support person, and every call that everybody makes, this is the first thing he says. So the YouTube clip has him saying this, I don't know, 100 times from different shows. And while it's kind of amusing, perhaps the more profound observation here is that this is the single most effective piece of advice ever given to a computer user anywhere and in all time, right? This is the most used thing for solving problems. So I'll take a quick poll, which I do whenever I give this talk. Who has, in the last week, restarted a machine or an application to cure some errant behavior, which was, yeah, okay, so most people. Usually it's everybody, but most people. And I think the important thing that we need to understand from that is why that works and what consequence that has for persistent programming. And the reason it works is because it discards all soft state. It keeps the hard state and it discards all the soft state in memory. And that's where most of the bugs lie in most of our programs, that we have, even 30 years on since the beginning of persistent programming, we are unable to build programs which are correct consistently for extended periods of time that we don't have to restart them. And so we have to face the issue of how are we going to deal with persistent soft state. So as opposed to going for the straightforward persistence by reachability method, I've adopted the scheme that Bill designed for NVM Direct, which is partitioning the world into different regions that are separated by hard boundaries, and using that to address this hard state, soft state issue. So we could do things like discard the soft state at uncontrolled restarts, and we could discard only when corruption is suspected. So soft state is a relatively easy problem to solve, but are we planning to introduce hard state into our persistent memory? We can't discard it, remember, so we have to deal with how to back it up, recover it, etc. And in persistent memory, all of the soft state and the hard state is built of the same stuff, right? It's just data structures in memory. It used to be that soft state was in memory and hard state was on disk. It was easy to draw the line between the two and throw one of them away. So in the model we've adopted, we continue to allow hard lines to be drawn. So we have a partitioned heap. Each partition is a self-contained data structure of some kind. The programmer gets to choose what's in one of the partitions, and that allows for enforced separation of states between things, and it adds some burdens for the programmer, but gives you the benefit that these partitions could potentially be used for a variety of different purposes, and one of those I suspect that's going to be important is the separation of hard and soft state in non-volatile memory. And then we, for the consistency and recovery model, we adopt a checkpointing notion on each of these partitions. So the partitioned heaps, the heap is partitioned into separate regions, which are explicitly either volatile or persistent. The programmer gets to create and decide where these regions are, how they're populated. Each of the persistent regions would typically be mapped from a DAX file in a sort of obvious manner. And then the code does object allocation within a specific region. We disallow cross-region references, except from volatile regions, to maintain that hard partitioning. And when the program begins, Java program begins as a single volatile region in the same way that there is at the moment. So that's completely compatible. So more graphically, we start off with a volatile region for the main program. The program can then map in or create persistent regions, can have references from volatile memory into persistent memory, and of course within a persistent region, references within itself. So all of those are legal, but we're not allowed to create references from persistent regions to volatile memory, nor from one persistent region to another persistent region. I say never allowed to create. There may be some mechanism provided to do this, which requires additional code that's not a straightforward pointer, in effect some kind of a handle with that forces you to supply recovery code. But that, in the simplest model, think of it as they're just disallowed. So how do we make stuff in regions? The idea is to have a notion of a current region in each thread, and that says where allocations are currently taking place. That allows us to wrap existing code to cause it to allocate within a specific region. And here's an example. We're taking the standard Java hash map, and we're wrapping it in a lambda, which is run within a method on regions that says, okay, run this code and run it so that the current region within the duration of this code is this, my region in this case. And that will cause the hash map to be allocated and initialized entirely within that region. So the persistence of a data structure then can be specified by the context, right? Where the context of the code that causes it to be allocated says whether it's persistent or volatile. If the context says we're in a volatile region, it's a volatile data structure. If the context says it's a persistent region, it's a persistent data structure, and we haven't had to interfere with the code in any way to say that. So then the model for recovery then is to have explicit checkpoints on these regions. So the program can invoke a checkpoint primitive, something that's supported by the virtual machine, which snapshots the state of a region and says, okay, if you fail from this point onwards, when we recover, we're going to recover back to the checkpoint. We allow, in this current model, checkpointing of one or more regions, which allows things to be synchronized against each other. But the normal case would probably be to checkpoint a single region at a time. And the case where you might want to do that, for example, is if you have an in-memory database and you don't want to checkpoint the whole database after every update, but you do want to checkpoint the log after you've made a record of every change that you've. So you could put the log in one region and the database in a separate region, and the log would be checkpointed more frequently. So the way to think of this is it induces a series of epochs into your execution. So the epoch is the period between two checkpoints of a region or before the first checkpoint. And in this graphic, we have time going left to right. We build some objects. We just take a checkpoint. And at that point, those objects are in effect immutable. If we want to change one, the change is then recorded in the second epoch, and there is a record of the object and its original state at the end of the first checkpoint in the first epoch. At each modification, first modification within an epoch, a copy of an object is made and kept in a separate piece of memory, and then all the subsequent modifications within that epoch to that copy. So, and the running program can only observe the most recent version of an object. You could build a much more complex model in which you have sort of meta-programming and you can see back in time, but that seems, at least for a first version, a little overcomplicated. Yeah?
How frequently do you expect new epochs to be created?
It depends on the data structure. For a log, it would be after every log update. We'll get to that. I have a slide. Okay, so recovery. So when a restart occurs, the latest epoch is uncommitted, we discard the updates in that epoch and roll back to the previous checkpoint. And then the program can continue computing from there. The locks are all discarded because the locks are handled by threads, and threads, in this model at least, are volatile. So threads do not persist, unlike in the OPJ work a couple of decades ago. How you manage checkpoints? Well, notionally they stick around until they're explicitly discarded. For systems in which checkpoints are infrequent, that discarding might be it might be something external to the program, in effect a utility that says, list the epochs and let me manage them and discard them, or we could provide an API to discard them and merge them. It's the model here, if you're familiar with the Mac OS and Time Machine, it's kind of a little bit like Time Machine in that you have a number of snapshots of previous state, and if you discard one of them, all that happens is that you merge two epochs together and the changes get amalgamated. So there's a fairly straightforward explanation for what discarding means. In principle, if we could keep them lots around, we could also provide the management tools to allow us to go back to any of the earlier epochs and restart from there. So to use this model, what does a programmer have to do? What is their burden? Let's imagine we've got an existing application that we want to port and make some of its data structures persistent. So the programmer would have to figure out where the partition boundaries were in the data structures and which parts were volatile and which parts were non-volatile. Add the logic to do the region creation and loading at the appropriate places. Wrap the parts of the code that create non-volatile objects in the method that makes sure that they're allocated in the right region, and then insert calls to checkpoint at places where the region was consistent and in a state to be safe for recovery. So how does that look in practice with a toy example? So imagine we start with a simple implementation of a phone directory as a map from strings to strings. We can make it persistent by inheriting from region, and that basically now says that all of its fields become roots of the structure in that region. And then the main method would look perhaps something like this. So we have a constructor here which takes the name of a file, a DAX file that contains our region data structure, and it either, if the file doesn't exist, it creates one and maps it, and we start with an empty region. If it does exist, it maps the existing one and connects it up so that the structure that was at the root of that becomes the new instance. And of course, you have to deal with errors in case the file doesn't exist or it's invalid in some way. How does the data structure get created on the first instance? Well, we provide an initialization method for regions that says, here is the code that's going to run on the first time the region is created. And that runs within the context of the region. So all of that code is executed, all the objects allocated within that are within the region in question. Yeah?
So is the object in its entirety allocated either in persistent memory or in volatile memory?
Yes.
So there's no way I can have one field in volatile memory?
Correct. Okay, so how would we then use this region? Imagine further down the code, we have a call to something that's adding an entry into the phone book. We now have to wrap that with the code that causes any allocations within that to take place in the appropriate region. And the code for that originally maybe looked something like this, where it's just checking to see whether the key already exists and adds it. The main thing we have to add is the checkpointing code to persist that state update. But that's not quite enough, because one of the things we have here is we're passing in variables which are in volatile memory, and we'll be storing references to them in a persistent structure, which is not allowed. So we have to add some copying code. And so in this case, I've added the explicit copying of the parameters to make new copies of the strings before they're installed in the persistent data structure. And conceivably, we could, so they have to be copied. Maybe for immutable data, that could be just done automatically because, well, after all, the programmer can't tell whether there's a copy or not in effect. Or perhaps we add some kind of annotation processor that does some copying for us, but that kind of only puts off the day of reckoning. Ultimately, the programmer has to have some involvement in this, I suspect. So how would you implement this? Here's a sketch of an implementation which is in progress. So one of the things you have to think about is that when you map the region, it could be mapped anywhere. You can ask for mapping at specific addresses from the OS, but in general, it's not a good idea to depend on that. So the region has to be position independent or relocatable. We've chosen to go for a position independent approach, again, following Bill's implementation of NVM Direct. We would also like checkpoints to be fast, so that they can be used relatively often. And if you checkpoint smaller stuff, you'd like that to be faster. So those are some desiderata for the implementation. The key goal here is to maintain steady state performance of long running programs. So we'll jump through hoops to make sure performance is as good as we can get, but we assume that crashes and recovery are relatively infrequent, and so that doesn't have to be super optimized. And we can do a little bit of trading of space for time because NVM is supposed to be cheaper. So how would we implement this in the VM? And the idea is, the common CS solution of adding an indirection. So an object, instead of being directly referred to by its address, would be referred to as an index into a table that was at the beginning of each region. And the table would then contain the offset of where the object's current incarnation lives. And in this model, the epochs grow from left to right. So as each epoch closes and is checkpointed, that piece of memory in effect becomes read-only. We map that read-only, and when we attempt to update it, we trap, copy, and install back pointers so that we can get to the earlier versions of the object fairly straightforwardly. And we can make all of this happen using self-relative indexes. Yes? Well, the thing is, if you go for more than 2, it's actually just the same for this particular case, right? It doesn't add any. Yeah, but you still have an indirection. I mean, the indirection is there anyway, and the extra cost of the back pointers gives you the ability to go further back in time. You know, again, if you think about systems in which you may have corrupted a data structure, you may want to recover backwards to the point before the corruption occurred and keep older versions around. And it also gives time for a backup system to make perhaps a copy of an epoch in a separate failure domain so that there's a recoverable version. If you have only 2, kind of time is tight. It may be that 2 is the right answer for some cases, but it seems premature to optimize for that specific case at this point.
Doesn't this go back to what you said about how we want to fix things by turning the device off and turning it back on again? But if your persistent memory is already corrupted, that doesn't fix your problem.
Right, but yes, exactly.
I think that's why.
Exactly. Thank you. That was a crisper answer. Okay, and I think I said everything from there.
I don't want to argue about this, but I don't think having all the data is actually going to help you. You want to know how to go back, you do a binary search and all the checkpoints. They will be inconsistent with respect to each other, and you get complete mess. Okay, so I don't know how all of this information will actually help you in the long run, practically speaking, but sounds like a cool idea. I'll do it.
Great. Well, then the user is just going to keep going back in time until it works again.
Yeah, but then he can never prove that that's even a valid state because he may have checkpoints that are not consistent with each other.
Yeah, so some notion of a set of checkpoints that's a consistent set.
Yeah, so the program can say I'm checkpointing these regions together. And execution is suspended until they're all checkpointed successfully. And that gives you the ability to say, you know, 2 of them were checkpointed at the same time.
The reason I ask the question is because, persistent memory is going to be priced at around the cost of DRAM. And, if you're going to be spending this much of persistent memory just storing, old checkpoints, unless you have a good swap thread that swaps it out to a hard disk or something like that, you're going to pay a lot of price.
So I'm not assuming this hits a solution like this is something for the next year or the next 2. The Java process moves slowly in terms of adopting things, and I'm assuming that over a longer period of time the price becomes a bit more reasonable. But ultimately, you have the properties of the memory of density and persistence, and you have to figure out what you're willing to pay for. And there may be, I want to make clear that I don't believe this is the only way to do this. There are lots of different ways to do this, and there are lots of different points, and kind of as a community, what we need to run is the experiment of providing different alternatives and see which ones address which market niches. I'm somewhat doubtful that there's a one-size-fits-all solution for something like Java here. But if there is, it will only emerge through a reasonable bake-off.
To be fair, let's finish it up.
I was going to say, to be fair, the case that being asked for is already available because you can just keep one checkpoint. So yours is a more general model, includes this is a special case.
Cool. Yeah. Okay, so we're currently in a fairly early stage. We have a definition of the model and some work towards understanding and implementing and verifying it. But the big open question is this a useful model? When is it usable? When is it not usable? What kind of mistakes do people make using this kind of model? How do you mitigate them? If that all turns out to have a positive answer, then we can get onto the technical things, which is, what do we have to fix? How do we find those things? What do we do with threads, objects with external soft state, things like file descriptors, which, there's an int, and that int only makes sense in the context of the current process. So we need some way of wrapping that in code that recovers or prohibits. We need to make it work. We need to make it fast. How fast will it be? in specifically what are the hits to performance, footprint, checkpoint latency, things like that. And one topic I haven't addressed, although we've done some thinking about, is how to enable software evolution, i.e. you have a persistent repository, you want to change your program, you want to change the data structure and evolve the two in sync. How do you do that? Bill has some approaches for MVM Direct. There's been some work in Java for this already, but that needs to be fleshed out in some detail, and I didn't really have time to talk about that. So we have a model. You have questions.
Last time I looked at the Java nmap, it's not demand based, which means it's sort of like program control. Program control versus DNA.
So hold on, before you go further, what do you mean specifically by Java nmap?
In other words, there is an nmap implementation for Java.
At the level at which users call it.
Yes.
And
it doesn't go out and fetch.
So that's not part of this.
Some sort of nmap underlying whatever your software layer is that actually is demand based. All the bytes are being.
Yeah, no. So firstly, the users would not be calling nmap at all. That's deep in the virtual machine is the mapping taking place, and the idea is to call into a.
So my point is, if that thing is slow, and it is, when is
Yeah,
it going
but-
to get speeded up?
So we don't need to use the Java implementation to implement this capability in the virtual machine. We just call directly into a DAX provided nmap,
Okay, that's
and that would be wrapped in all of the stuff that makes it look like a region, and just presents that as objects up at the user level. The Java nmap is unrelated.
Java, you're going to do Java pipelines.
Yeah, exactly. And I don't want to predicate all of this on fixing various properties of the JDK.
We have time for like 2 questions. Are you going to store Java class metadata with the region? So you're going to have that just in the program and assume that you always run the program the same.
My feeling is that there has to be some amount of metadata in the region, even if it's a cryptographic hash of the class files, just to summarize which version the objects relate to, and that we compare that when we actually do class loading. There are some really tricky questions here around classes and class loaders, which again, I did not have time to go into. But I think it's important to have, it would be nice for each region to have a complete self-contained description of the versions of the code it was built against. And it also helps with evolution.
I have another one.
Sure.
So the other thing in your talk, you were talking about sort of preserving the current status quo in terms of Java software, because there's so much of it.
Yeah.
It's the same problem in C++ with the standard library, which is also doesn't scale.
Okay.
Right? And so I think of an exabyte of fine-grained allocation and initialization and deallocation from all these wonderful type models that people are so friendly with. And from working with the high-performance computing people, I noticed that they allocate enormous built-in arrays and deallocate them in constant time. And it's like, that scales. And that's why they do it that way. And it's like, they couldn't imagine doing this with Java. They couldn't imagine doing this with C++ with the standard library. So there's a dinosaur here that's going to die. Question is, what are we going to do?
That's not my problem. I would run screaming from that problem.
All right, thanks for being here.